actually play favorites with radial velocity in this talk, and I have to be fair-handed about all. So I'm going to try. I'll probably fail a little bit, but I'm going to try. Okay, but before we get started, just a reminder that when we talk about exoplanet discovery techniques, we're often talking about very different regions of the galaxy when we talk about the different techniques. When we talk about things like radial velocity, we're probably talking about the nearest 100 parsecs to the sun. When we're talking about microlensing, you're probably staring directly into the galactic bulge and the stars between you and the background lensing star. So often when people talk about habitable zone planets or Earth-like planets, we are really talking about a very small bubble around the sun. Sandro gave a very good talk this morning about the migration processes. And of course, we would like to observe planets as they form, and possibly with ALMA, we're actually doing that now. It's kind of pretty fantastic. But most of the planets we have discovered tend to be not around the youngest stars because of selection biases. Those are hard systems to find planets around, but they tend to be around more mature stars after the disk has dissipated. So the migration processes have played out. Of course, there are other dynamical processes that are still continuing. But in some sense, the planetary systems we're discovering today have echoes of those migration processes, but they also embed other dynamical processes in them. Just because we haven't seen a full-scale diagram yet, a reminder that there was a question about what happens if other stars come and interact. Well, in about 40,000 years, a star does come through the Oort cloud. Right? This has happened to the sun before. This has probably happened to a lot of stars. So interactions are not uncommon, but the question is how close they are and what the dynamical impact of those interactions. Just talking about our own solar system, so the planets are to scale. Obviously, the distances are not to scale. It's very clear there are three types of planets in our solar system. There are the rocky terrestrial planets, the gas giant planets, and then the ice giants. And of course, we got rid of the ninth one a decade or two. But the inner system, the rocky planets, they are very different, right? Mars and Mercury are much smaller. Venus is a near-Earth twin, roughly the same radius, roughly the same mass, completely different outcome because of where it is, how close it is to the star. So not only does the mass and radius matter, but the installation history of that planet matters a lot. So when we talk about discovering planets, different techniques are going to have different biases and different strengths in discovering these. The topic that will come up again and again, of course, is the habitable zone. And one thing to be very clear about is that a planet in the habitable zone does not mean a habitable planet. Right? There is no prerequisite that such a planet must have water. It just means that given the right atmospheric composition, such a planet could have liquid water on its surface, and therefore is potentially an attractive target for the search for biosignatures. There's a bias because we have liquid water on our planet, and we have life, and therefore we go, oh, it seems like the chemistry we know indicates we should look there, and that's where we're looking, right? But it does not mean that there will even be an atmosphere, and even if there's an atmosphere, it does not mean that there will be water. You actually have to show and demonstrate with spectra that there is water in the atmosphere, or there is liquid water on the surface before you can claim something about it being habitable. The first exoplanet discovered was actually on a pulsar. This is a very rapidly rotating neutron star. We'll talk about this a little bit more. But one of these planets is actually the size of, or the mass of Mars. One of them is actually even smaller. Millisecond pulsars are fantastic clocks. And we'll talk about why this was perhaps the reason the first planets were actually discovered on us. The first exoplanet discovered on a sun-like star, 51 Pegasi b, was discovered with the radial velocity technique, which we will also talk about. But this is actually really, in some sense, what opened up the field. The pulsar planets are rare. They're weird. They actually shouldn't exist. Any planetary systems that existed around those stars should have just been completely demolished during the supernova explosion. So likely these are planets that somehow reformed after the explosion. Right? But they are planets. The pulsar planets are genuine bona fide planets. And this was the second planetary system that was discovered, and it was around the sun-like star. So here is the exoplanet discovery technique chart. There will be a quiz. So there will not be a quiz. Dynamical techniques generally rely on the fact that the planet is tugging on the star in some way. And you can use timing or radial velocity or astrometry to detect planets tugging on the star. So the mass of the planet matters a great deal there. The mass of the star matters a great deal, right? Because this is a dynamical interaction between the star. Microlensing relies on the mass of the planet, lensing a background star. Imaging is literally taking a picture, but of course it's hard. Photometry is the shadow of the planet as it goes in front of the star, or the light of the planet dimming as it goes behind the star, which really only works if you're in the very red or the thermal infrared. Generally, the planets we look at are pretty cool. Photometry transits have been really a workhorse. The 6,000 something planets we know, the majority of them were actually discovered by the photometric technique or the transit technique, even though it was not the first of the techniques that we used to discover exoplanets. It certainly has been the most productive in terms of finding candidates. And then there's a whole bunch of techniques that got essentially in 2018 labeled indirect miscellaneous, but they're not necessarily that indirect or any more miscellaneous than any of these other techniques. Harish is going to talk about star-planet interaction, for example, radio emissions, this white dwarf pollution, things falling onto white dwarfs that are planetary remnants or planets themselves that then pollute the white dwarf, and we can detect the spectral signature of those. There's debris disks, these protoplanetary disks. ALMA might have the potential to actually look at the flow of material into the protoplanetary phase and be able to discriminate planet and moon formation if enough observation time and fidelity exist. So this is our playing ground today for planet detection techniques. So the first evidence of exoplanets may actually have been 100 years ago. This is Van Manen's star. And those two little dips that you see in the spectra, these top and bottom spectra are just calibration spectra. But those two little dips you see here are the calcium to H and K lines. This star, which is a white dwarf, it should not have any metals because the metals all just sink. They don't have much of a lifetime unless they're supplied continuously or constantly, has a huge signature in calcium H. And the thinking now, and of course nobody thought about it when this spectra was taken in 1917 or 1919, the thinking now is this is planetary pollution or a debris disk, a post-formation material from planet formation falling back into the star. So white dwarf pollution has emerged as a signpost in some sense of planet formation. And in fact, there are some candidates where there is mid-infrared emission or excess mid-infrared emission around white dwarfs, which is very likely to be because of giant planets. There's one transiting giant planet, in fact, known around a white dwarf. And it's only in recent years that that field has really begun to find planetary systems. So just like the pulsars, which are neutron stars, the white dwarfs also tend to have planetary systems. So here is a nice little graphic of how our discovery of planets changes over time. And of course, in the 1700s, 1800s, just like Uranus and Neptune. And then we hit, nothing much happens for 100 years now, right? But then we hit about 1992. We find the pulsar planets, the radial velocity technique is beginning to discover planets. And in the early 2000s, the transit technique starts beginning to be productive. And very quickly, upon the launch of Kepler, the transiting exoplanets just like go into a boom. Radial velocity exoplanets are still being discovered, but then more and more, the radial velocity instruments are being used either for blind searches around the nearest stars or to confirm the masses of the transiting planets. Nature does not make planets in all sizes equal. The most common planet on shortish period orbits might actually be a type of planet that doesn't exist in the solar system. A mini Neptune, about 2.5 Earth radii. There is a gap here, it's called the radius valley, between the terrestrial planets and the mini Neptunes, or a sub-Neptune. And that radius valley has different hypotheses for its origin, one of them being photoevaporation. So not only is it how planets form, in what shapes and sizes they form, but what happens to those planets? What does a star do to those planets? So more and more, we're beginning to think of planets not just as planets, but part of a system, which is what it is, right? It's part of a system with a star. and the properties of that star matter a lot. Today, we're going to pretend that stars are our friends. Tomorrow, we will talk about why that is not true, why stars are messing with it. But for today, stars are our friends. A quick reminder about some fairly basic SI units and why it matters. So remember how the second is defined in the SI system. It's a certain number of transitions of the cesium-133 atom. This will change in our lifetime. It's going to get better. It's probably going to become strontium or probably even nuclear clocks, right? But it's only going to get more precise. It's already very precise. It's only going to get more precise. Okay, so the second is defined as essentially that number of transitions of the cesium-133 atom. The speed of light is a constant. So if you measure the speed of light better, we're always doing better experiments. Question for the students, what changes? If you measure the speed of light better, what changes in it? Meter. It's the only thing that can give. This is defined in the cesium atom. This number is a constant, so the meter changes. Okay? So our fundamental unit of measurement in the SI system is not length, it's time. So we should measure everything in time to get the most precise answer, right? And that's what we did, right? So if you put a clock on a star, which is what a pulsar is, and you time that pulse, as the planet tugs on the star is going back and forth from your perspective, right? The timing of that pulse arrival changes. And you have an exquisite clock sitting on this pulsar, and you're able to detect the pulse delay due to the tug of these planets or planetary systems. And the better your clock, the more your sensitivity to low mass planets. And pulsars are excellent, excellent clocks. Longer the observations, the more sensitivity to both the lower mass planets as well as long period planets. So this is the crab. It pulses about 30 hertz. People actually looked at it and seen it pulse by eye. But millisecond pulsars are pulsing at much, much faster rates, right? Which makes them very, very good clocks because you get pulses a lot, and also the stability of those pulses is extremely high. So punchline is we can measure time and frequency very, very well. And this is why, in retrospect, perhaps it's not that surprising that the first planets we discovered were around a system, the pulsar, where we could make these measurements at these high levels of precision. Today, if you tell somebody, oh, tell me about discovering a terrestrial mass planet in the habitable zone, they'll be like, oh, that's pretty hard. The first planet discovered was that mass. Special situation, very special situation, very special precision, very rare, but nevertheless, the first discoveries. Okay, so we can measure time and frequency very well, to the point where our clocks are now so good that over the distance of the clock, over the height of the clock, you can measure the gravitational redshift. That's pretty amazing. So for about a decade, there was a competition between the pulsars and people. Not that the pulsars knew there was a competition, but we won, right? The human-made clocks are now better. So we really can measure time extremely well. So we can measure frequency much better than we can measure length. So what are we going to do for the rest of this talk? We're going to measure length, because the clocks don't exist on stars other than pulsars, right? Yes, you can say we have p-mode oscillations, but those are quasi-periodic. They're not very precise. They kind of suck, right, for doing this kind of precision. In fact, they get in the way. So you have no choice. You have to come up with a technique that doesn't rely on the clocks. Sometimes you can rely on clocks when you have an eclipsing system and there's a planet around it. There's been a few discoveries that way. But generally speaking, we have to measure things that we can actually access, not be stuck on the fact that frequency is more precise when you can't actually measure time or you don't have a clock. Okay, so, but we can cheat, right? Astronomers cheat all the time. This is TRAPPIST-1. It's a system of 7 planets transiting. It's amazing, right? We just happen to be in the right orientation with respect to the TRAPPIST-1 system that 7 planets are transiting. We can't measure frequency, but we can measure time. So we've measured the time of these transits over many, many years. And because these 7 planets are in resonance, they actually tug on each other. Because they tug on each other, they're dynamically influencing each other. And because they're in resonance, that influence is pretty large. And we can invert that timing, that transit timing variation, the TTVs, into masses. It gives you a unique set of masses if you solve with enough data those TTVs. Right? And you can see where the TRAPPIST-1 planets lie with respect to solar system planets. They're very close. It's telling you that the terrestrial planet formation process is fairly similar. Of course, specific metallicity matters, but some M8 star that's barely a star is forming the similar-ish in density type of planets as exist in our solar system. And we can do this again because we are exploiting a little bit the precision of timing here with the transits. Not quite in the same way as the pulsars, because you have to fit the transits and get their center midpoint, but in a similar way. Okay. The other thing that's happened over the last few years is this thing has launched, finally, after 20-something years of waiting. But it has been amazing. So the light curves we're getting from James Webb Space Telescope from the transits are kind of simulated textbook level light curves, right? So this is, 5 years ago, you'd be like, oh, this is clearly a simulation. It's not. This is real data. Here's the primary transit. Here's the phase curve. Here's the secondary eclipse as the planet actually goes. Okay. So one of the questions we want to answer, and of course we care about giant planets, and of course we care about mini Neptunes, but the hard measurements that we want to make, which is driving some of the technology and some of the new missions, is also how do we measure biosignatures? How do we measure the spectra? How do we actually get enough signal to noise that we can discriminate and tell whether there's a biosignature on such a planet? And in fact, where are these planets that we're going to make these measurements on? Like, don't we have to find those first? Probably have to. Or you have to build a self-contained mission that will do that. Which brings us to the habitable zone, which is stellar mass dependent, stellar history dependent, planet mass dependent, planet obliquity and rotation dependent. But calling it a habitable zone is a bit of a simplification. All of these physical parameters matter. At the same time, it's not a crazy simplification. There's some region around a star where liquid water could exist on a planet, given the current atmospheric properties. And that region exists for stars hotter than the sun, and that region exists for cool M dwarfs that are much cooler than the sun. They're also very faint in the visible. So of course you want to wonder, why should you bother? These seem like hard targets. This is the 10 parsecs surrounding the sun. All those red dots are M dwarfs, and everything else is either a sun-like star or a planet. And you can see that the M dwarfs overwhelmingly dominate. 70-ish% of the stellar population of the galaxy is an M dwarf. So if you're interested in the planet formation process, you cannot wipe out 70% of your target stars, right? Unless your question is very narrowly about planets around G2 type stars, because we know our planet has one. But we are interested more broadly, I think, in the planet formation processes, and the disk mass scales down in these stars as well. So there are interesting things that happen about what kind of planets you can form and how they migrate and evolve. Okay, so the radial velocity method, one of the sort of first techniques, very simple. Planet and star are orbiting their common center of mass. If the planet orbits at 1 year period, the star is doing the same orbit at 1 year period, but at a much smaller wobble, and you're only measuring the radial velocity, the velocity in your direction. So if the planetary system was like this and the planet was going like this, you'd measure nothing. If it was projected towards you, you would measure everything in between, right? So there's a Sinai degeneracy always in radial velocity. So for a sun-like system, Earth around the sun, that's about 8.9 centimeters per second over a year. Same planet around a mid-M dwarf, as a star is much less massive, to be a 1/5 the mass of the sun, much less luminous, so the habitable zone moves inward, so the periods are now 30 to 50 days instead of a year. That Doppler semi-amplitude rises to about 1 meter per second. So This is hard, very hard. This is hard, but less hard. Problem is, these stars don't actually give out much light in the visible. You might have to go in the infrared or go to large telescopes or have very efficient instrumentation in the optical. So the other thing about M dwarfs is the two closest M dwarfs to the sun are Proxima Centauri and Barnard star. Proxima Centauri has 2 planets at least, discovered by the radial velocity technique. Barnard star had a claim of a long period planet that did not hold up. It was actually stellar activity that feeds into tomorrow's talk about how stars mess up everything. But more recently, espresso has shown that there are 4, likely 4 terrestrial planets around Barnard star. So the 2 closest M dwarfs to us actually have terrestrial planets, which is telling you something about the statistics. Planet formation is ubiquitous, and low mass stars are capable of forming rocky planets pretty easily. So how do we actually do this? And Francesco, I'm sure, will dive into this much deeper, but sort of at the 0th level, you have to take a spectrum, a high resolution spectrum of the star, and you have photospheric lines from the star, and you're looking for the wobble of those lines. Right? But what does 10 centimeters mean in terms of velocity, right? We know what 10 centimeters mean, but you're not actually measuring velocity. You're looking at a line and you're seeing how it changed on your detector. And for a typical spectrometer, that 10 centimeters is some small 1,000th of a pixel or something like that, which if you translate it is 4 or 5 silicon lattice spacings, atom lattice spacings. So you're trying to measure on a star a velocity that is basically just a few silicon lattice spacings on your detector, which is a little crazy that we're even trying to do this, except we could do it. We are doing it. The stars are just getting in our way. Another way to look at this velocity and to sort of understand the kind of measurements we're trying to make is this. This is the velocity we're trying to measure. On a star, if we weren't almost able to do it, this would be crazy, except we can, right? So you don't do this with one line. You do this with many, many lines. You don't just use one absorption line. You use thousands of absorption lines, and you combine them into one velocity or a set of velocities, depending on how you want to select these lines. The other technique is, so radial velocity was really about the Doppler velocity that's coming towards you, right? And you go, well, why do we bother with this? Why not just look at how the star moves on the sky? Just on the 2D sky, the planet will pull, the star will move, right? You don't really have a Sinai degeneracy in this because, even if the planet was this way, it would go this way. If it was this way, the star would go that way. The reason is this technique, while very attractive on paper, requires a precision that's even crazier. 30 microarc seconds. Or 0.3 microarc seconds is what you need to be able to pull this off, right? But this has changed in the Gaia era with the launch of the ESA's Gaia mission. So in this case, what are you looking for? You're basically trying to say, how does this star change with respect to all the other stars around it? If you have enough other stars, or if you have a reference frame that's stable, you can say, aha, look, this is wobbling, and I have detected this wobble on sky, just on the 2D sky, and planet. In reality, that's not what you see, right? There is annual parallax as the Earth moves around the sun. This thing, the spacecraft's not actually on Earth, it's on L2, but L2 kind of does trail the Earth, right? There is proper motion. There's a star is moving over time. So you don't fit the astrometry just for the planet. You actually have to fit out distance, proper motion, and distance and parallax are degenerate. Distance or parallax and proper motion, and the residuals of that parallax and proper motion are really the wobble that you're trying to detect. So, seems like this should be possible. It's possible, but there's a lot of gotchas. What you're really measuring is the shift in the center of the light of that star, right? Just measuring a photocenter shift. There's a planet, and you can say, well, come on, the planet basically has no light. Doesn't count. And it's going to tug on the star. The planet's going to do some weird orbit. This thing is going to do a little bit of an orbit. That's what you're looking for, right? This is what you'll get because the universe is messing with us. Two stars, roughly equal luminosity, orbiting each other. One is slightly dimmer or brighter than the other. The net result will look like a tiny orbit, which would be the same as that induced by that. So you go, aha, I have discovered this amazing planet. You discovered a binary star. And half of the stars are binary stars. So what do you need for that? You need radial velocity. You actually have to go get spectra and convince yourself that it wasn't a binary star. And we actually did this survey, and other people have done this too with previous Gaia data releases. 80%, 90% false positive rates, right? Most of the stars are binary stars. But one or two of them actually do pan out. For example, Gaia 4b is actually probably the first bona fide Gaia confirmed exoplanet, or 10 or 11 Jupiter masses, which was confirmed with radial velocity. This becomes very interesting because late this year, perhaps sometime next year, Gaia's next big data release comes out. And if the numbers are to be believed, it will double the number of known planets. Largely, it'll be giant planets, but that's very interesting from a dynamical perspective. At that point, you will need much better vetting or some sort of radial velocity tool at large scales to be able to quickly tell, good God, that is another binary star, or wait a minute, this is actually real. Okay, photometry. This is just the shadow of the planet as the planet happens to pass between you and its own star. The Earth around the sun is 80 parts per million. That is very, very hard to do from the ground. Possible to do from space. And this is an area that the Kepler space mission was supposed to shine in. And the Kepler space mission, for all its amazing discoveries, failed in some sense in its core mission, which was to tell us the fraction of stars that host Earth-like planets in the habitable zone, eta Earth. The stars ended up being noisier than they had assumed, and the mission went through its nominal 4 or 5 year cycle, but didn't continue beyond that because of reaction wheel failures. So we never quite got a handle on eta Earth that was super precise. Somewhere between 15 to 30% with error bars of 15 to 30%. Turns out this number matters a great deal when you're trying to actually design the next mission. Same planet around a mid-M dwarf, much, much deeper transit. So the M dwarfs emerge as very attractive targets because they're the most numerous stars, but also their velocity amplitude is larger, the transit amplitudes are larger, and if there was a planet, the astrometric amplitude would be larger. In fact, Gaia 4b, it was a K dwarf. So what is this? This is for the students and the postdocs. So in groups of 2 or 3, can you tell me what is happening in this transit? That is what the transit should look like. This is what the transit looks like. This is what's that? Why don't you all discuss for a minute and we'll talk about all the possible hypotheses. So if you haven't talked to your neighbor as one of the students or postdocs, please group up and have a minute of discussion. Talk first, we'll discuss first. Okay. Who would like to volunteer possible answers? There are many answers, right? So yes. Is it a star spot? That's one possibility. What are the other possibilities? Exomoon, that would be a big exomoon, yes. But yes, it would be a little smaller. It could be an exomoon. What else? I heard somebody saying planet, 2 planets crossing. This is a star spot. Right? So the planet is occulting the star spot. And the spot, of course, is darker than the photosphere. So the flux decrement during that occultation is less than it would be if the spot was not there. But of course, it's still below the continuum. Right? So this particular planet, TIA 3884, is actually on a polar orbit, and it's continuously crossing a polar star spot, a giant polar star spot around an emblem. So this is a cool system for many reasons. You can get the spectrum of a star spot, you can think about helium escape, et cetera, et cetera. But it's also a frightening system if you are thinking about timing this transit. If you're trying to precisely find the midpoint of this transit, oh my God, it's going to cross some star spot. But it's also frightening because if you try to do it for some other system where you did not have this level of fidelity, it might still be crossing some star spot that you were subtly not aware of. It will also mess up the transmission spectra. These are things we will talk about tomorrow. Today, we are pretending stars are our friends, remember? Okay. So photometry is, in some sense, of course, ground-based photometry is super awesome. But in some sense, the discoveries have really been enabled by the fact that we've been doing this from space. Okay? Kepler's search area, it was like a pencil beam, 105 square degrees, but like a pencil beam, 4 years, stare at a single patch of sky. TESS is a different strategy, 27 days in each patch, patch it together, very different goals. The fraction of Earth-like planets around sun-like stars. Nobody will call Kepler a failure, but it did fail in its primary mission. We still do not have a precise answer on eta. Perhaps Plato will give us that, or one of the new missions. TESS, very different goal. Oh my God, we're launching this $10 billion James Webb Space Telescope. What are the targets it's going to look at? TESS was successful in that, but it's never going to find eta Earths. It's never going to give us statistics on eta. That's not what it was built for. It only stares for 27, 30 days at any patch. So it does beg the question, TESS is like this little 10-centimeter telescope, which is making all these amazing discoveries. Kepler was big. It does beg the question, why are we going to space? Space is expensive. Space is awesome. But compared to ground stuff, space stuff is different. It costs more money. 2 things. One is when you focus a star, whereas when you defocus a star, the blurring you see is very different. When you're focusing a star, yes, you'll get the tip-tilt motion of those Zernike polynomials because of the atmospheric turbulence. But when you defocus, it's actually an image of the telescope pupil, and you'll actually see all the turbulence there. And this light will kind of flicker around all these spaces. So defocusing kind of works up to a point, but you don't get as good precision just with defocusing as you would just with a stable environment like space. The other problem is more insidious and is really caused by the atmosphere itself. And this is called atmospheric scintillation. It's basically the same phenomena that leads to twinkling of stars, right? There's light coming in to the top of the atmosphere. There are all these turbulent cells, and they're randomly going to put light in or out of your telescope. So even a perfectly stable star is going to look like its photometry changes because of the atmospheric scintillation, because of the atmospheric turbulence. Adaptive optics doesn't cancel this. Right? Adaptive optics will make your wavefront quality better, but it won't it can't get you photons that you lost because they were scattered in or out. Right? This thing scales with telescope diameter, but slowly. You have to go to much bigger telescopes. It also scales with air mass, so you have to be at low air mass as possible, right? But if you can do this, and we've built things that diffuse the light in deterministic ways, and in fact, other spacecraft like Cheops, etc., do the same thing. But if you can do this, you can actually get very good photometry from the ground. So this is some of the best photometry we've obtained. So this is the photon error bar, and this is the scintillation. This is the problem from the ground. Even with large telescopes, your scintillation noise is always going to be bigger. The aperture didn't buy you, it bought you a lot, right? The scintillation noise does go down as g to the power 2/3, but it doesn't buy you the photon noise back because your photon noise is also going down. So this is why space wins, right? Because a 10 centimeter, 20 centimeter telescope from space can actually do better photometry than your 3-4 meter telescope from the ground, as long as you have enough photons. Obviously, if it's some 18th magnitude star, your dinky 10 centimeter telescope is not going to work. Right? You do need to do that. Yeah. But you know, we've actually shown that you can actually get down to Kepler level precision from there. You just can't do it for 4 years at a time staring at a patch of sky. Right? You'll do it on the nights you'll get clouded out, et cetera, but you can do it far cheaper and almost at the same thing if you have a specific target that you want to go after. So ground and space work together in this regime in terms of photometry. Okay, here's another example of a recent paper. This is V1298 tau, 50 million year old system. I said early on that young systems are extremely difficult because they're both active, so it's hard to get the photometry right, but also it's very hard to get the radial velocity of these systems because the stars are active. Here again is a similar trick to the TRAPPIST-1. 8 or 9 years worth of photometry from the ground show us those TTVs. And we can invert those TTVs to get masses of these young planets. And with the mass, you now get density, which means you can actually look at how photoevaporation is sculpting the planets. So when you bring multiple techniques to bear, you can really begin to tease out properties of these systems. Okay, next question for the students and postdocs, working groups. Can you think of ways in which a photometric transit can affect the measured astrometry? And in what ways could combining astrometry and photometry help with discovery or characterization of exoplanets? Please discuss. You want to join one of the group? Join the group behind you. Okay. Need more time? You need more time? All right. How about the first one? How can photometric transits affect astrometry? During the transit, the light center will shift, yes. But remember, stars are very small in angular diameter. I mean, yeah, giant stars are big, but normal main sequence stars are pretty small, right? So a transit around a normal star should not mess up your astrometry too much. A transit around a single star should not mess up your astrometry too much. So in what ways could the astrometry be messing up? binary star, okay? And this actually happened to me recently, and I was like, you have got to be kidding. This cannot possibly matter, okay? Two M dwarfs, one of them has an ultra short period planet, which is a giant planet, so the transit is deep, like 10% transit, okay? And ultra short period planets, so duty cycle is about 10%. So 10% of the time, Gaia catches a transit. And at that point, the relative flux ratio of the stars has changed. And you think you have an astrometric signature when you didn't. Okay? So insidious stuff that makes sense when you put it all together, but multiple techniques do have to be thought about together. Okay? So what about this one? In what ways could you combine astrometry and photometry to help with characterizing exoplanets? Yeah, very good. Astrometry for a long period transit will give you mass, right? For a short period transit, it won't at all because it's not sensitive to short periods. It will give you mass. The other thing it could give you is if you have a short period transiting planet, there might be a giant planet outside it that is not transiting because the probability of the transit very much drops with distance, right? But astrometry can reveal the giant planets in the system that you have planets in. We are just beginning. We're just at the very tip of the iceberg in being able to use all this stuff, right? Because the next Gaia data release will really sort of be the opening in some sense of this technique. Okay, so what can spectroscopy give us? All kinds of things. I'm a spectroscopist at heart. Radial velocity combined with transit gives you planet masses. Radial velocity alone does not give you planet masses. There's a sign of ambiguity. But when you have a transit, you know the inclination. It has to be close to 90 degrees unless it's very, very close. At that point, you know the inclination, so the velocity directly gives you mass. The transit gives you radius. Assuming you know the radius of the star, which for most main sequence stars you probably do. Okay. Put that together, get density. Aha, now you can pretend that you're a geophysicist, right? You have density, you can talk about comparative exoplanetology. In reality, we have very little information compared to our solar system colleagues, right? We can't actually go and study the internal composition of these planets, but we can study the composition of the star and make some assumptions. You can answer questions about multiplicity, obliquity, dynamics of the planets. If you have transiting planets, radial velocity follow-up is now pretty necessary because otherwise, how do you get the mass? Without the mass, what are you actually doing? And of course, you need very precise masses to constrain the composition. The other reason you need it is we are thinking about flying all these telescopes in the future that will do imaging. You want to find where those planets are. Where are the terrestrial planets on the nearest stars? There's probably 100, 200 stars max that you can image. You want to spend your time wisely. Probably want to find out where they are. Of course, spectroscopy also gives us atmospheric properties of planets, but this is a tomorrow story because this is remember what the light is that you're detecting. It's the stellar light, right? You cannot decompose the star from the planet. They're part of the same story. Okay. The technique we did not talk about yet, gravitational microlensing, is a little different from the ones we have talked about. Its physics is, of course, different. But all the other ones we've talked about are repeatable phenomena. You can go verify your observations. Gravitational microlensing at an individual system level is not a repeatable thing. You have a source star and a lens star, and the alignment from your point of view has to be very, very close as that lens star passes in front of the source star. The mass of the lens star will lead to a lensing event. It looks like an amplification of light. Really is just space-time curvature. And if there was a planet around that and the caustic alignment was good, you will also get amplification with that planet. So the bigger amplification signal in some ways is your signpost of, hey, look here. And the tiny amplification, or not so tiny amplification, that is sharper, that sits on top of that is your, wait a minute, there's a planet, right? So this is nice because if you were just looking for that, that's a much narrower, shorter time span. This kind of gives you a heads up that, hey, let's start looking here intensively to monitor these. So there are many dozens of microlensing systems known already. But what makes this very interesting is that it probes areas that the other techniques cannot easily probe, like the 1 to 2 AU region, 1 to 3 AU region around stars, Neptunes, super Neptunes, Jupiters. That Gaia now is going to become sensitive to Jupiters, but not so much the Neptunes. Also sensitive to Earths, just depends on the alignment. But what makes this really interesting is this is the field of view of the Hubble Space Telescope. And this is the field of view of the Nancy Grace Roman telescope. So we are in for a paradigm shift in quality and amount of imaging. And coupled with this dramatic field of view increase is something called the Roman Galactic Bulge Survey, which is going to look at the galactic bulge, all those fields in the galactic bulge for more than a year, and in sets of 72 days. And the full survey area will be imaged every 12 minutes. And the microlensing events are much longer, so you're not going to miss out much. So the galactic bulge is interesting because that is where your density of stars is highest. That's where the chance that you'll have these overlaps is highest. This is also probing a region of parameter space that radial velocities are not easily probing. Radial velocities need bright stars. This is looking at a population that is very different in metals, very different in galactic archaeology, right? So planet populations that are distinct in some ways from what they are around the nearest stars. Let's talk about imaging. In some ways, this should be the easiest thing, right? Take a picture. What are you messing around? Just take a picture. This is a very nice image from recent JWST observations of Epsilon Indi AB. That bright star is Epsilon Indi A, blocked out. But why is it so hard? Why has it taken so long to do this? It's actually been a process over the last 10, 12 years of slowly getting the technology good enough that we can actually image giant planets at very far distances. And this is HR 8799. You can see the 4 planets around the HR 8799. This is an actual movie of a planetary system in orbit, right? It's pretty amazing. Those are also pretty far out planets. None of them are close. I mean, Jupiter would be like right in there or something. Right? So it's like hundreds of AU. So how do you actually do this, and why is it so hard? What you use is a coronagraph, and coronagraphs were invented to study the corona of the sun. You have a telescope, and you form an image with that telescope, and normally your detector would just be here when you were taking a picture, right? It's an image plane. But you put an occulting mask here instead of your telescope, and then you'd re-image this onto the Leo plane. And what this occulting mask does is, it's of course blocking light, but it's also a mask or circular aperture, so it's diffracting it as well. And the light from the star diffracts out into airy rings further out. If you just image everything back, there's still too much light. There's light in those airy rings, right? But you block out those higher airy rings, then you re-image it, you get something where the center is dead, or not quite dead, but very low. But the planet light that's coming from an angle is not blocked. And the planet light gets through. You're still attenuating the planet light, right? But you're not attenuating it anywhere as much as the star. So this is sort of the 0th order approach of what a coronagraph does. To me, it makes much more sense to think about this in Fourier space, right? And in Fourier space, this is your telescope aperture, and this is 1D. In reality, of course, it's 2D, but 1D is a good illustration. Telescope aperture, so a square rectangular thing. Fourier transform of that is, of course, a sinc function, right? And then your occulting mask, if you built it well, it's a nice apodizing occulting mask, is some Gaussian that goes from 1 to 0. So you multiply that with the sinc function, and you get this masked image that you then have to Fourier transform again for the Leo pupil, and it looks like this. And you can see the power is out here. And then you put this mask, which is your Leo stop that essentially removed the rings, and you've cut out all that extra power. Your on-axis throughput now sucks, which is what you want. You want to block the star. Your final image has very little starlight, but much more of the planet. The reason it's taken so long is to do this well, to get the 1,000,000 to 1 contrast that you need for a Jupiter, requires an adaptive optics system, which is almost entirely diffraction limited, very high stress. It requires control on wavefronts that is exquisite. And 1,000,000:1 doesn't quite cut it. Right? There is a better way. It's called a star shade. Instead of using a coronographic mask inside your instrument, you essentially put a mask very far away. It's almost like sticking out your thumb. Except you stick out your thumb many fraction of an AU away. If this were a perfect circle, you would have gained nothing, because the light will diffract around the edges of that circle and interfere at the exact middle and cause something called the Poisson spot. So the entire game with the star shade is to build its edge in such a way that that Poisson spot is canceled. The coronographic masks are not achromatic. They're essentially working on interference principles. You're recombining light. So bandwidths are 10%. So they kind of suck. They're throwing away most of the light. The star shade is a lot more achromatic. So of course, what are we flying? We're probably going to fly the coronagraphs, right? Because from an operational concept perspective, this thing has to maneuver. It has to get between you and the star. It could take like many months, right? Superior technology, but not less expensive and not any easier to use in an operational perspective, right? So was it the right decision? I won't comment on that, but these are considerations that have to go into any real imaging mission that you build. Okay, so what do you actually want to find, right? I mean, obviously you want to find life, but you're not making images of the planet's surface. You don't have that kind of resolution. So you are going to rely on spectra. You probably want to find things like oxygen, methane. Sometimes people think about the red edge of vegetation, the fact that chlorophyll reflects very heavily in the red. But again, is that a quirk of our own biology or is it fundamental? Those are interesting questions. At least on the Earth, the CO2 varies over a year. It's called a Keeling cycle. If you actually have the sensitivity, you can look at those sort of things as well. But you need to first image the planet and get its spectrum to do any of these things. So the biosignature of a habitable planet, in reflected light, has a very sharp Rayleigh tail, just because blue light is getting reflected, scattered off its atmosphere. And then you can see things like oxygen, water, ozone, methane, at least on Earth. And in transmission spectra, which is something we can do right now with JRBST, but we don't have the sensitivity to do it for Earths, you can see other things, but then you worry about clouds. Clouds mess up transmission spectra, hazes mess up transmission spectra, stars mess up transmission spectra. Reflection spectra are much better, but you need to spatially resolve the planet before doing that. Okay, so what is 10 billion to 1 contrast? It's rough equivalent of there is a firefly in there. Actually, even this I'm off by an order of magnitude. It's dimmer than this, right? That's what we're trying to do. It's, again, like that tortoise, a little crazy that we think we can do this. We actually are probably up to 10 to the 8, 10 to the 9. Right? But this is what it takes. Almost perfect wavefront control. Optics of such high quality that scattered light is very low. Deformable mirrors that can absorb or take up the rest of the scene. So the next great observatory, and great observatory is a type of observatory. It's not saying that the observatory is great, right? Hubble was a great observatory. JRBST was a great observatory. Chandra, it's a type of observatory. It's like, it makes transformational science, some NASA lingo. Is the Habitable World Observer. We don't quite know what it looks like because it's very much in trade studies, but it probably looks something like one of these things. Some 6.5 to 8 meter telescope. We know how to build 6.5 meter telescopes. We build JRBST, right? But we haven't built one that does 10 to the 10 contrast. Pretty tough. But if this thing works, this is the kind of images one should produce, right? The star is nulled out. There's some giant planet out there, and there's this little speck of light that is an actual terrestrial planet in the habitable zone, which you then, once you find it, have to sit on to get some very low resolution spectra, and then try to figure out where this biosignature. High resolution spectroscopy of terrestrial exoplanet atmospheres with even the great observatories are not going to be possible, but maybe they'll be possible for M dwarf planets with the 30-meter telescopes. Because at some point you just run into a I don't have enough light problem that the 30-meter ground-based telescopes do solve. But then you still need good spatial context. Okay. So what's coming up is HWO in space, timescale of 15-ish years, maybe 20 years. The 3 30-meter class telescopes, of which the EELT is happening, and I hope the other 2 happen. And potentially a mid-IR interferometer in space called LIFE. That's another mission that Europe and IISER are discussing doing, which will be very complementary to HWO. Because the thermal infrared gives you different sort of things, different parameters, and then if you put together, really help you nail down the atmospheric properties. But this is the slide I will stop with. This is our current demographical understanding of planets. And it encodes many of the things we have talked about. The fact that the pulsar planets, very close, but one of the first, radial velocity, quite sensitive to close-in planets, kind of peters out when you get to very far distances. There are not that many known radial velocity planets at roughly 1 AU around the G star. And that's where we would like to be, not that many known. Transits all over the place, right? I mean, but not that many at long periods. Probabilities drop, or maybe 1 or 2. For imaging, we're moving in from the other side. Right? It's easier to image things further away, and harder as you get closer and closer to the diffraction or few diffraction limits. All the imaging planets, look at the masses there. There are tens of Jupiter masses. Also because the contrasts needed are not quite there yet. But this is the parameter space that imaging will begin to fill in. Radial velocity is beginning to get in that way. Transits are beginning to go there, fill in that. And then astrometry, if Gaia DR4 lives up to its promise, will really populate this parameter space quite well. So I'll stop here. Yep, questions? Yeah, that's actually a very good question. Yes, the signals, as long as the planets are not interacting with themselves dynamically, they're not in resonance, it's basically like you can add up the signal. So you'll see the Jupiter signal of 12 meters per second over 11 or 12 years. But on top of that will just be an addition of Earth's signal. So as long as the planets are dynamically not interacting with each other, it's just adding up all the signals. So you will see all of them. What is your second question? Yeah, that's a very good question. So with radial velocity, if you were on that plane, you would see nothing, right? So if you were orbiting like this, you have to have some directionality towards it. Astrometry is not quite like that, right? With astrometry, say you had a planet orbiting, transiting, then the star gets displaced in one direction, but it still gets displaced on the sky, right? Because the planet is pulling it one way or the other. It just won't get displaced this way. So you are sensitive to different angles with astrometry. So it's because the 2D motion on the sky because the radial velocity is kind of a 1D thing, right? And this is a 2D thing. So the 2D motion actually captures all possible angles. Yeah. Yeah, that's great. So such planets exist, right? We do have escaping atmospheres. We've only really detected them without significant, crazy amount of effort in Lyman alpha, for which you need to go to space, or helium-10 which is an infrared line. Neither Lyman alpha nor helium-10 are in the typical optical bandpass of radial velocities. So you probably won't see anything. If you look very carefully, you might be able to detect some, in transmission spectroscopy, some elements like iron. But the tail is too tenuous. No. Just for exoplanets. Signal to noise. It's a signal to noise argument of how faint the planets are and what the aperture of the telescope is. If you, for Earth-like exoplanets is what I was talking about. It just turns out that even with very low read noise detectors, the amount of time you have to stare at these things becomes incredibly long. Impractical from the mission perspective. For Jupiter's, perhaps, there are going to be high resolution instruments on HWO. They may not necessarily be behind the coronagraph. What about the? Yeah. Yeah, that's a great question. No, it's a problem. You're going to need the radial velocities anyway, because if you don't get the mass, you cannot invert your scale height arguments and really determine the properties of the planetary atmospheres. The thermal imaging missions, like LIFE, they actually overcome that because the thermal emission is less sensitive in some sense to the scale height of the atmosphere. So yeah, we're going to, even if we find these planets, we're going to have to go back and do the radial velocities. Wait. Yeah, but sure, but those are giant planets that are very young, right? These are mature, likely to be mature terrestrial planets of a few. In thermal, yes, but in reflected light in the optical and near infrared, yeah, that's tough. You need the mass for that. Yeah, that's a good question. So typically what we use is something called the Rossiter-McLaughlin effect, right? So if it's an edge-on system, then it first blocks the blue receding side and then the red edge, and then you see a system. In this case, it's a little faint to do the RM, but it's because of the fact that it crosses this spot every transit, and the rotation period of the star is not necessarily the same, right? So it almost has to be that pole one orientation. It's the only configuration where the star's rotation period could be different, and you still end up with a spot cross. Yeah, well, that's a really good question. So actually, we're limited by the stars, right? The stellar activity, I would in fact claim, and Francisco should fight me on this if I'm wrong, I would claim that the current instruments are good enough to find Earth-like planets if the noise was Gaussian, right? you don't need to be at 10 centimeters to find a 10 centimeters per second signal if you can observe many, many epochs, if your noise is Gaussian. The problem is the stellar activity makes the noise extremely non-Gaussian, extremely red or pink. And then you are you have to overcome the stellar activity problem before you detect it. Mm-hmm. Yeah, so that would be true of the sun. The fully convective M dwarfs have magnetic fields strong enough that they end up pinning the star spots to the poles. And the star spots can last many years. So, yes, but that's also why the magnetic fields are so much stronger. And no, it's the same spot. It's the same spot. Because we have observed this over many, many months. It's always the same spot. Extremely high. And some are known to last decades. TW Hydrae, for example, has a spot that's decades. Yeah, I think the theoretical models struggle with making those planets in the first place. So it was a surprise that those planets existed. They are almost certainly reprocessed material that have recongealed into planets. There are some theoretical models. But the thing is, it's the observations and the data that have to drive some of those models, right? So for the pulsar itself, yeah, right. No, I don't think so. I think it's more about the dynamics of how the material re-aggregates into a planet. Because there is this violent process, right, that blows apart the planetary system, and then somehow things re-aggregate. There have been some theoretical investigations, but I mean, there are only so few systems, it's hard to do anything. Yeah. Yeah. So the exoplanets may not necessarily be in the galactic bulge. The galactic bulge is, in some sense, the source of the source stars. But the lensing system is between you and the galactic. It's still in a very different environment than us, but it doesn't have to be that. It doesn't have to be in the galactic bulge. It just has to be between us. So what you're really doing is you're increasing the density of the light sources behind you, so that you have increasing the chance that one of them intersects something between you. The dynamics are going to be very different. It's in some sense cluster environments. There could be a lot more stellar interactions happening. It could be that they disrupt planetary systems. It could be that the demographics are completely different, right? Lensing will tell us. For the coronagraphy. Yeah. It does. It does. And that's why I said the bandwidth is very limited. So what you do is you put some filter, like a 50 nanometer filter. That's all that. Oh, the star shade screen. No, that one is a little less achromatic, right? It's more a distance issue. So you could always, I mean, you still have a filter, some sort of a filter there, but the depth of field, because the thing is so slow, right? I mean, you're very far away, so depth of field is extremely high. So within your instrument, your depth of field is enough. It's been tried on binary systems that are fairly close. So there you can pin, you can use one of your binary stars as your reference and then see if the other is moving. Of course, you don't know which one the planet is around, but people have tried that. And I think the ESO gravity instrument is pretty spectacular even at getting spectra of planets because you can actually coherently integrate. Once you're doing interferometry, if you're locked to some star, you can coherently integrate if you know where the planet is. And there are some HR 8799 spectra of gravity that are pretty spectacular. So yeah, it's possible. Of course, yeah. Yeah, so the question is, do you need to discover it before, or do you go do it after? If you discover it before, you can have a more efficient observational system because you can look where, and these are expensive telescopes, right? So if you do it after, you have the advantage that maybe you know the period. And that makes it a lot easier for radial velocity. Rather than doing a blind search across multiple periods, if you say, roughly the period is here, then the confidence in your signal is much higher because you're looking in a narrower range. So I suspect the real answer is we'll do both. I'm not sure there is one. There's a lot of concern, a lot of gnashing of teeth, but I don't know if there is a coherent strategy, right? There should be one. And the strategy should be we need to push the radial velocity technique, at least for these 100-something stars, really pound away. But I think if you add all of the radial velocity instrumentation on the planet today, we may not be there yet. Mm-hmm. Yeah. So I think for those systems, I mean, look, we use radial velocity on those systems because there's nothing else, right? If you can do it in any other way, you should do it in any other way for the young stars. But sometimes there is no other way, right? So then we have gotten pretty good at Gaussian processes decorrelating with activity, with rotation period. There are spectroscopic indicators in your data that you can decorrelate against. But yeah, if you can do it with the TTV way, that's in some sense better. Also less expensive. Remember, radial velocity is extremely expensive in telescope. Any last questions? So O3 shows up very nicely in reflection in the UV. It doesn't show up as well in reflection, right? Because you're essentially glancing the light off the atmosphere at fairly large scale heights. So O3 just has these very nice absorption features in the UV. That is a strong indicator. It also has some longer wavelengths, but not so much. O2 is better. All right, that pause sounds like time for lunch. Thank you all.